Hello everyone and welcome to our presentation on the evaluation of the mechanical properties of 3D printed PLA in two printing orientations. This is presented by Sindra, Haygreave, Sophie, Sriram, and Anika, and our advisor is Dr. Starostina. I'd like to start off this presentation by discussing what PLA is. Polylactic acid, also known as PLA, is a thermoplastic polymer that's formally obtained by the condensation of lactic acid with the loss of water. Its pellets are heated up and spun into a filament for 3D printing. PLA is one of the most frequently used thermoplastics in 3D printing. It's biodegradable, and relatively environmentally friendly. Mechanical and physical property values of materials are needed for finite element analysis calculations in mechanical engineering. PLA is a leading biomaterial in medicine, replacing petrochemical-based polymers. So why additive manufacturing? The construction of a three-dimensional object from CAD is a new and emerging form of manufacturing known as additive manufacturing. It generally refers to 3D printing since it constructs objects layer by layer. Its applications include medical implants such as heart walls and retainers that are mostly 3D printed. The aerospace industry uses 3D printing for their spacecraft parts, and additive manufacturing is generally used for rapid prototyping. It's also important to note that the mechanical properties are usually inferior to parts manufactured through traditional methods such as injection molding, casting, and others. On this slide, you can see the printing parameters we used to 3D print the samples. The most important value to note is the build orientation because that differed between the samples we printed, so a vertical sample and horizontal samples.
For sample preparation, we created a CAD model on the software Onshape that reflected the ASTM D638 standard samples for the tensile testing kit. For the dataset, we 3D printed our samples on the Prusa i3 MK3S Plus printer with a natural color filament as a control variable, since a difference in color will change the dimensional accuracy and, more importantly, the strength of the print. In the experimentation process, we created 12 samples. 6 of each were printed in either a horizontal or vertical orientation, and within that 6, they differ in thickness by either being 3.2 millimeters or 7 millimeters thick. Next slide. As said before, we use tensile testing, which measures the mechanical properties of the material through a stress-strain diagram, namely the ultimate tensile strength, the amount of stress a material can undergo before it experiences surface fractures; yield strength, the amount of stress a material can undergo before it experiences permanent deformation; Young's modulus, an intrinsic mechanical property related to the slope of the linear region in the stress-strain diagram; and finally, ductility, or the amount of deformation that a material can undergo before it experiences surface fractures. We use the optical microscopy, or the Keyence optical microscope, to detect surface fractures, and we use X-ray diffraction courtesy to EAG to detect the partial crystallinity of the 3D printed samples. Segueing into our next slide. For the X-ray diffraction results, we can see if the samples or filament has a crystalline structure if there are sharp diffraction peaks. But in these two cases, it displays a very smooth graph and exhibits amorphous behavior because of those. Because of this, the material properties that the samples exhibit can be traced directly to the printing parameters and not the crystallinity of the PLA. For the mechanical test results, we can see that the vertically printed samples exhibit a brittle behavior, while the horizontally printed samples exhibits a more ductile behavior. For the potential causes of difference, in the vertical sample, the direction of the tensile test is working in conjunction with the direction of the layer lines, and thus it will be far easier to experience surface fracturing. Meanwhile, for the horizontal sample, the layers do not work in this suspected case and mainly focus on the 45-degree raster angle, which doesn't conform nearly as well to the tensile test and isn't much of a point of weakness as the layer lines in the vertical test. For the mechanical testing data, the Horizontal ultimate tensile strength mostly compares with what the manufacturers best understand for the bulk properties of PLA. However, it highlights the extreme difference of the ultimate tensile strength in the vertical direction compared to it. We also reported the yield strength of the sample, which not even the manufacturers or currently studied literature would report. And as for the Young's modulus and ductility, it exhibits a fine split due to the difference in print orientations. This is highlighted when you consider how Young's modulus is properly attributed to the base material properties.
Annika, we cannot hear you.
What do these values mean on this graph?
Well, okay, I can narrate. This is what we observed in an experiment. We calculated the fine split as indicated in the previous slide, and it looks like we do observe the fine split between two orientation, number one, and fine split between two sizes. So we can explain perhaps the split between orientations, but the sizes we're looking into it, and our next the remaining of presentation will talk about it in details.
Hello?
Yes, Annie.
Is my mic working?
Now it's working.
Can hear you,
Okay.
Annika.
Wait, did you guys already go through this slide or?
I did, but you can go over it. That's fine.
I was just gonna say, here are the average mechanical properties for both sizes and orientations. As you can see from the data, it looks like we have a very fine split for the mechanical properties for each orientation and each size. And we're currently looking into the details in the fractured surface to understand this split.
Here are the fractured surface diagrams for the vertical and horizontal orientations. Looking at the horizontal orientation, we can see that it's built, like the layers of the 3D print are built up from the print bed, while for the vertical orientation, it's standing up straight on the print bed. And because of this is one of the reasons why our horizontal orientation tends to be more ductile and the vertical print tends to be more brittle. Next slide. Here are results for our optical microscopy of the fractured surfaces. Because the vertical sample is more brittle, as you can see on the side view here, on the leftmost side, this fracture is very smooth. There's not a lot of roughness. Meanwhile, here is our center view. That is a top-down image of the entire fracture. And on the rightmost side, you can see our 3D reconstruction of the fracture. From the 3D reconstruction, we're able to obtain line roughness values. Next slide. And from these line roughness values, we can compare the roughness of the sample for different sizes and different orientations. When we compared the vertical orientation, two sides of the vertical orientation, we found that size did not play a major role in the roughness values, as the RA and RMS values were pretty similar. Next slide.
Okay, so these are our horizontal fracture images. Our first image is, again, a side view. You can clearly see a bunch of peaks and valleys from the side view. You can see how rough it is just from this. Our second image and our last image are both top-down views. In the second image, I have a red circle. It highlights a sort of peak and valley that you can see. You can mostly see kind of like the part that's closer to the microscope, and then the darker part is a lot further below. And then the fourth image is a 3D reconstruction of the whole image. And our third image, we have, our fourth image is actually a stitched image. Our third image is our 3D reconstruction with, again, the same peak and valley that you saw in the second image. So essentially, all these images go to show that we're expecting our horizontal fracture to be more ductile and more rough. Next slide. So in this slide, we're going to be comparing our 3mm horizontal orientation and our 7mm horizontal orientation. For our average line roughness values, you can see that in the X direction, the 7mm horizontal value is a lot rougher. Same goes for the Y direction. You can see the same with the RMS line roughness as well. The X direction seems to be rougher in the 7mm horizontal sample, and the Y direction also seems to be rougher in the 7mm horizontal sample. So what we're seeing is that the 7mm horizontal sample is a lot rougher than our 3mm sample. Next slide. In this slide, we're going to be comparing our 3mm horizontal and vertical samples. So essentially, it's the same thickness this time, but different print orientations. What you're seeing from this is that the horizontal values are a lot rougher than the vertical values for both average line roughness and RMS. On top of that, we can also see that the X values are a lot rougher than the Y values for, again, horizontal and vertical models. And essentially what we're seeing overall is that horizontal models or horizontal orientations are a lot rougher than vertical orientations.
So these are our results for the comparison between the 7mm horizontal sample and the 7mm vertical sample. As you can see, our results are very similar for the 3mm sample, and it's fairly consistent with the vertical sample being much smoother than the horizontal sample. Next slide. Here are conclusions on the fracture surface observations for the two sizes and two orientations. For the same size, our measurements suggest that vertical orientation fractured surface is smoother than the horizontal fractured surface, and our results are consistent for both the sizes, so for both the 3.2mm samples and the 7mm samples. And this is consistent with our mechanical measurements, indicating that vertically printed samples are more brittle, therefore fracturing in more smooth fashion, while horizontally printed samples are more ductile and are fractured in a more rough manner. For the same orientation samples, our results show that for vertical samples, size does not matter, while for horizontal samples, a thicker sample results in a rougher fracture. However, we are still questioning if size matters. For our future plans, general expectations suggest that size should not matter, at least for bulk materials such as metals, alloys, and polymers, and within a certain range, but future work is needed for clarifications. We also need to articulate our hypothesis for a size influence and figure out if it is a genuine observation. We also plan to correspond our mechanical testing data in slide 10 to the fractured surface data for the same orientation but two different sizes. And we also plan to continue an extensive literature search on the influence of print orientations on mechanical properties, as well as on a possibility of sample thickness influencing mechanical properties for 3D printed materials. Next slide. Here are our references. And lastly, we would like to thank our parents for all their effort in driving us to and from the lab. We would also like to thank our advisor, Dr. Starostina, for guiding us through our research. We would like to thank ASDRP for providing us with the necessary resources to carry out our research. Additionally, we would like to thank Santa Clara University for performing our tensile testing and for EAG Laboratories for performing the X-ray diffraction. Thank you. Any questions?